So we have one more pattern here. I think we can probably cover this first part of this pattern in the next 15 minutes or so. And that'll leave for us for next time the second half of this pattern. We'll talk about the implementation artifacts of this pattern, and we'll also talk about a couple more patterns. And then we'll get ready to move on to something new. So what we're going to do now is we're going to kind of take the proxy and stretch it out a little bit and put something in the middle, and that something is called the broker. The broker pattern is a pattern that appeared in the Poster 1 book, and then it's been revised various times along the way because the original description needed to be enhanced as people got better insight about what brokers really were. And so we learned a lot about what brokers were over the years. So the context for this is some kind of system with multiple objects that are potentially remote. They may be remote, they may not be remote. And these objects have to interact with each other synchronously or asynchronously. And in the case of Android, of course, this would be over binder RPC. The problems here is we don't want application developers to have to think about a number of accidental and inherent complexities. We'd like them to not have to worry about these details to the extent possible. We don't want them to have to think about low-level message passing, in other words, taking their native data types and manually encoding them, linearizing them, doing all the things that proxies do. They shouldn't have to worry about that. That's basically what proxy does, by the way. But there's some other things we'd like them not to worry about either. We'd like them to have to not worry about various types of diversity or heterogeneity that pop up in the underlying infrastructure. They shouldn't have to worry that the client side and the server side are written in different programming languages, Java versus C++ versus Prolog versus C. We shouldn't require them to worry about what operating systems these platforms or these applications, clients and servers are running on. They shouldn't have to worry about the networking protocols, the type of the hardware, and so on. That should all be shielded and encapsulated from application level concern. We'd also like to try to shield them as much as possible from other more inherent complexities, things like partial failure, security implications, maybe latency, other kinds of things that may be issues in a system that's getting bigger. We'd like to try to shield them as much as possible. You can't always shield people from these things. If the network gets cut by a backhoe, you may just have an outage, right? It just may not be a way to get around it. But often there's ways of taking alternative paths or being able to have replicas or redundancy or so on built into the system. And it shouldn't be the application developer's job to think about this. I've written a lot of stuff about this topic over the years, and you can take a look. There's many, many sources of information on my website about it. So what's the solution? The solution is to basically separate out the communication concerns that are sort of in the infrastructure from the application concerns and use a broker in order to kind of mediate between those two realms, the systems, the infrastructure kind of stuff, and the application kind of stuff. Now, how is that done in Android? Well, you probably know by now it's done using the binder and the AIDL mechanism. So we implement a binder object that the clients can't get to directly. We get a proxy back to that via the various means we've talked about using on-service connected and so on. And that client proxy is then used by clients, like activities, to invoke operations. And those operations then travel through the system after first being converted into parcels by the underlying proxy. And they travel through the binder framework and pop out the other side to the stub, where they're converted back into data types and passed to an upcall. And that upcall is what actually does the real work to do the logic that's defined by the service binder implementer developer, and then they can pass the results back if it's a two-way call. So the key thing here is that the binder is combining a bunch of things. It's combining proxy, it's combining broker, it's combining activator, it's combining adapter. There's about 8 different patterns. We're just talking about broker. As we'll see later, broker is actually a pattern language. There's a bunch of other things that come along with it for the ride. So the intent of the broker pattern is to try to connect clients with remote objects in a way that allows the broker to mediate the interactions with the clients to the remote objects without requiring the client or server developer, application developers or service developers to have to know anything about how this works underneath the hood. So you would typically end up applying this pattern if you want to be able to support local or remote communication in a consistent way. You want to be able to make the handling of various fault issues shielded from the application developer. You want to shield the application developer from things like memory management, connection management, data transfer, synchronization, concurrency control, so on and so forth. I should probably list some of these things out. Low-level system details, such as memory management, data, let's see, connection management, synchronization, and threading. You know, you think about it, there's a whole pile of things that you've got to think about if you write all these pieces of code, and you'd like that to all be hidden from you as much as possible. Different implementations of brokers, by the way, go to different extents to hide you from some of these things. So here's basically the structure of this pattern, and I'm pulling this particular structure from a couple of different places. I wasn't really happy with any one description of this stuff from the literature out there. So here's one I kind of came up with based on a few things. So basically you have a client, which is like an activity in Android, the guy making the call. You have some kind of infrastructure, like the Binder RPC framework, which is broken up into requesters that send things and dispatchers that receive them and process them and upcall them. You then have demarshallers, demarshalling and marshalling, and they do the serialization and deserialization. That's what we typically think of as being the proxy. And then you finally have the guy that does the real work, which is called a servant in this particular context. Sometimes people call these things executors, but we'll call them servants for now. So those are the main components that you would typically find in a broker. And if you take a look at this paper, it gives you a flavor of this. It uses slightly different names, but it's the basic idea. Here's a picture that kind of illustrates how all this stuff works. A server registers an object either through some kind of configuration script, like a manifest file, or dynamically through some kind of API. It says, you know, here's an object that needs to be accessed remotely. That's what the starts out, so that everybody knows that exists. Then a client is going to get back an object reference or some kind of service identifier to this object, and it's going to go ahead and invoke an operation on it via a proxy. And it'll call this on the requester. The requester will set up a connection if it doesn't exist already, do the marshalling, send the data over. The data goes over via the broker. The broker might or might not be a separate process or a separate thread. These might be libraries that are linked together. It might be some intermediate mediator that is separate from the client process and the receiver process. It really depends on a lot of different things. Scalability, fault tolerance, memory utilization, battery power, all kinds of different considerations come into play. The dispatcher takes the request, basically works with the demarshaller part to crack open the data, extract out the message fields, turn them into data types, and then make an upcall back to the object. The object does its work, the method on the object does its work, and then it sends the response back, which goes back by the inverse path of how it got there in the first place, most typically. So those are essentially the dynamic steps with the broker. This obviously maps very nicely onto what's going on in the context of Android for a whole bunch of different reasons. And we'll talk about those next time when we talk about implementing this pattern in the context of Android. We'll look at the steps and the interactions. There's a whole bunch of different consequences of using this particular pattern. A bunch of good things. Location independence. You don't really know or care where the objects reside. They might be in your address space. They might be someplace else, as Nolan was talking about. So that gives you more flexibility. There's a clear separation of concerns. The infrastructure, the broker implementations, doing all this heavy lifting for you, so you don't have to worry about it in your application, unless there's a bug in the broker, but that's another story. And if you make changes to the implementations, the clients typically shouldn't be affected by that. And then there's also a whole pile of other benefits. If you implement brokers using standards, like Corba, for example, or other technologies in that space, like SOAP and so on, then what you'll end up with are ways of being able to get portability. You'll be able to get modularity. You get portability because you'll have common interfaces that are standardized through open specifications. You will get modularity because you can break your system up into pieces and you can test them individually. You get reusability because you can reuse both the broker infrastructure as well as services you build on top of it and objects you build on top of it. And all of this stuff has many, many, many patterns galore to make it all work. There are some downsides. For many years, especially in performance-critical environments, environments where the right answer delivered too late becomes the wrong answer, those kinds of mission-critical or safety-critical environments, people had a perception that brokers added too much overhead relative to hand-coded solutions. That has changed over the years. People have gotten really good at implementing very high-performance brokers, but sometimes if you're in certain environments, there may be too much overhead. Potential issues with reliability. Reliability is something that's often very hard to define in a completely generic and common way, because different applications have different reliability needs that are often not well served by a one-size-fits-all solution. So if you're not careful, you might end up compromising your reliability requirements to use something that's defined off the shelf by a broker, and it might not work as well as something you might handcraft yourself. Having said that, it takes a lot of work to handcraft these things yourself. And of course, anytime you start having layers of stuff involved and many different components, you quickly realize you've got a big issue as far as debugging and testing. The minute you've got distributed anything or concurrent anything, there's a lot more stuff running around. And you've probably already seen that as you're trying to debug your programs here. If something goes wrong, is it because the service didn't work right? Is it because the client didn't work right? Is God help us if Android's not working right? That might happen once in a blue moon. But you just have to be very thoughtful about where things are going wrong. There's a number of known uses of broker. Once again, the early days were sort of procedure call-based brokers, DCE, ONC, or SunRPC. Corba, probably the predominant example of a broker. Corba is so much a broker is its middle name. It's the Common Object Request Broker architecture. It's right there in the name. And then, of course, nowadays we get Android. I want to talk briefly about this whole issue of manually doing things versus automatically doing things. And as I kind of alluded to before, there's always this paradigm shift that occurs in any domain, any field, as things that used to require human expertise are gradually overtaken by automation. I was just reading the other day that apparently it used to be the case a couple years ago that humans aided by computers could beat computers at chess. And now it's apparently no longer the case. Computers are so good at playing chess that you don't need humans to help them play a better job than a human playing with a computer can do. So I thought that was interesting. One more thing humans aren't good at, right, compared to machines. I would argue there's an awful lot of things humans aren't as good at machines at, but there was a time when they were. And whenever people tell me those things, and by the way, as you go through your technology career, you will see the following meme pop up over and over again as new stuff comes along. Because at first, it won't be that good, and people will poo-poo it, and over time, it'll get better and better and better. So my favorite example of this phenomena, which is really at the heart of the innovator's dilemma that Clayton Christensen liked to talk about, is the famous story of John Henry. Does anybody remember who John Henry was? What was John Henry's great feat?
He laid on railroad.
He was a railroad worker, and his great thing was he's a real big, strong guy, and he could take a sledgehammer or an axe, and he could sort of single-handedly chisel through massive amounts of rock to make railroad tunnels. And so there's a great story where John Henry goes out and he competes against a steam drill. And in those days, the technology wasn't very good. And so, they have this contest. The day starts, the steam drill starts drilling, and John Henry starts, chopping away with his sledgehammer. And the steam drill keeps, breaking down, and they have an army of technicians running around trying to fix it. Sounds a lot like software sometimes. And so what happens? Does anybody know what happens in the story? Who wins? John Henry wins, right? He gets through that mountain first. But what happens to John Henry? He dies, right? So there's a metaphor there that says through superhuman effort, you can sometimes beat the machine at certain points. But it's often not worth it, right? You may pay a big price for doing that. So the real thing to do, of course, is not to try to beat machines. It's to write better machines, right? That's how you make it big. Be wealthy, popular, and famous. Okay, so that's it for the lecture for today. What we'll do next time is finish off broker implementation, and then we're also going to talk about observer, because that's sort of the last, I think that's maybe the last big pattern that we've been talking about in all this stuff. And then we'll get ready to start talking about content providers.